Hey everybody. Hope you're doing well wherever, whenever you are. Um, I, I something messed up on the recording of this one, and so I had read through the problem and then failed to set it up. So I think what I'm gonna do is I'll start over and I'll read the problem again just for this video. But just know I've already done some like 5 or 10 minutes of analysis. So anyway, that hope you're doing well wherever, whenever you are. Uh, and howdy, did I say that? We're here on day 10, Advent to Code 2015. And before we go too far into it, I did find this algorithm, so I'll include the link if anyone's interested in reading about it. It's called the held carp algorithm. This was from yesterday's day 9. I'll add the link to day 9 as well. Basically, what it says is these guys found an algorithm that solves that traveling salesman problem in 2n to the n squared time, whereas normally it would be n factorial time, which is what I solved it in, n factorial. And this is still an NPR hard problem. It doesn't change that. But you can see how big of a difference it can make for especially large values. The caveat being it requires n2n space to hold the computed values, right? Because what's happening is the reason why this is faster is they can they're doing dynamic programming, and so they can, if they've seen segments before, they know instead of calculating those segments, they can like finish it off is the way to think about it. But you now have to track all those. It's like an array dynamic programming solution. If you read through it, you'll kind of see how it works, but like I won't go into the details here. The idea though is you kind of do some early work of saying like, oh, can I figure out distances between some chunks, and then that simplifies the process. Again though, it requires a lot of memory to solve that, so for larger ones it can become a lot of memory, right? But you can see the difference. I think I said this was 2 quintillion in my previous recording of this before I failed, but the idea is it's a lot, right? This is huge compared to this. Notice though how the quote unquote more efficient, the faster solution, the lower ON, takes more time until you get to 8, n of 8. And that's just something to keep in mind is sometimes, so for our problem, the fastest was the actual brute force. Just try them all, 5,000 of them. If you did it this way, it actually was more intense because, and why was that? Is because this early setup, this n squared setup to get you to the point where you can do it in 2 to the n, or sorry, the 2 to the n set, you do a 2 to the n setup that allows you to do the n squared part of it. I think it's the way it works. Anyway, the whole point of this is to say we were right. I think I was right that it was a brute force problem, and there is a more efficient way. It's still NP hard though, and for our solution, it turned out that this was correct. If the solution had been larger, like say it was N13, then we may have, it would have definitely been more efficient to use this, assuming we had enough like memory to hold that much space, right? So that's the other consideration with there. So we'll just leave it at that. Okay, so with that, let's go on and we'll work on day 10. And I have read through this and started analyzing it. So the recording, I just had a problem with the recording. Hopefully that's all fixed. But here, so I'll read it again. Elves look, elves say. Today the elves are playing a game called Look and Say. They take turns making sequences by reading aloud the previous sequence and using that reading as the next sequence. For example, 211 is read as 1221s, which becomes 1221, 1221s. So this took me a minute to grok, but we'll read through it and I'll help make sense of it. Look and say sequences are generated iteratively using the previous value as input for the next step. For each step, take the previous value and replace each run of digits, like 111, with the number of digits 3, followed by the digit itself, 1. So it gives us some examples. 1 becomes 11, and then 11 becomes 2 1. 2 1 becomes 1 2 1 1. 1 2 1 1 becomes 1 1 1 2 2 1 for these two right here. And I had to do this it took me a little while to grok it. So you probably, maybe this way is better because I'm not staring at my screen trying to figure it out and I'm actually able to talk to you about it. So 1 1 1 2 2 1 becomes 3 1 2 2 1 1. Okay. So the idea is they're going to give us this puzzle input, and we're supposed to go start from that point and find the 40th after you've done it 40 times. What is the length of the result? And here's where I left off. I was looking at this look and say, here's the sequences. You can see they get really long. But it didn't show. Oh, notably, it talked about John Conway. John Conway introduced it. He's the Game of Life guy. Conway's Game of Life, if you're familiar with that. Anyway, it said that it grows indefinitely, but it doesn't grow in a great. I mean, it gave us this polynomial root, which is, crazy. It didn't seem like there was any way in after reading this, and you can read through it too, or maybe you've seen this before and there's a more efficient solution. It's not clear to me that there's anything more efficient than just going through it and doing it, meaning find the digits, like group up all the digits and create a new number, and then doing that 40 times, right? So it would, so I think we just start doing that. So I've got my input here, and so we'll say let mute cur equal input dot trim, because I don't think I want any of the new lines or anything like that. But then I'm just going to do like a for we're going to do this 40 times, and we're going to and so what is the we're going to do this 40 times? We're going to create a new number from this, right? So I think I do want a vector. And then we're going to return cur.lane at the end when we're done. So before I forget, we'll probably do that in part 2. Or not. Sometimes part 2 changes, but the last few days I've gotten it wrong. Okay, so what do we want to do? We just want to loop through all the and find the groupings. So we'll say let like in, I don't know, let pause equal 0. So this is where we are. Let next equal 0 as well. And then we'll just do like while cur pause equals next pause. Oh no, cur next plus plus. What is this? Okay, so at this point we've now found it. So we want to do like next dot push. Next dot push. Cur end. No, cur pause. Ooh, we have strings and characters. I actually want to. Isn't there like a digit? 2-digit? So it wouldn't be a car, it would be a. We're working in U size, so there could be a lot of these. Okay, so we'll always be working on numbers, which is not the most memory efficient. But what we say is, so we'll go through and we'll say, hey, for our current position, we're going to do this. We're going to find it and then push those on the end. And then eventually when we're done, we're going to do cur equals next. Okay, but we have to do this in a loop. So we'll say while pause less than like that. And then we need to do, after we're done with this one, then we'll say pause equals end equal pause. Something like that. I kind of just want to do it once. See what I get. But let's talk through it for a second. So to get the current one, I'm going to get the input, trim cars, turn those into digits, and then collect those. And then I'm going to run through this process a bunch of times where I create a new one, start at the beginning, and I say, well, pause is less than curling. So if I ever get past the end, I know I'm done. And so I say, while the current position is equal to the end, I'm going to increment in. So I'm going to go until I find a different digit. Ooh, I had to do while, and you also do like end is less than cur.lane. Probably something like that, just so I don't go off the thing. But then once I've gone through there, or I've hit the end, I'm going to do that. I'm going to put the count and the value. And then I'm going to move my pause to the end and make the end the pause and then go there. Pause. Eventually I hit the end, and then I do cur equals cur.next. Okay, I'm going to try it once. And I'm going to print line cur just to see what it looks like. Okay, 3 1 1 3 1 1 2 2 2 1 1 3. Okay. 3 1 1 3 1 1 2 2 2 1 1 3. Okay, I think that did it. That's right. Bueno. Okay, and that was pretty fast, 4 milliseconds. Neat, right? You also John Conway talking about the sequence. Yeah, it is Conway's Game of Life. Okay, now start again with the digits of the puzzle input. Apply this process 50 times. What is the length? Is this is a video? Okay, I won't go to the video, but I've probably seen this before. It sounds familiar now that I've used it. Maybe it's a number file. Okay. Now, okay, I just need to do it 50 times. Okay. Is it just a lot of disk? A lot of memory, maybe? Yeah, what is this? 5 million? I don't know how you calculate memory usage. Okay, I mean that one wasn't too tough. I think the biggest issue with this one was just knowing anything about it. I had never seen this before. Again, I don't know that there's a better way. It might be interesting to see if people have spent time trying to solve this more efficiently. Like, do you know the length? I think it did mention up here. I honestly do not even want to try and do the math. The length of growth is about 30% per generation. Like, I wonder if you could calculate this number. Someone did figure out the real root polynomial. So you could probably actually figure it out. I just don't want to do it. But you could also say, am I approximately correct? Like, you know, it grows about this much each generation. So you could say, am I within some approximate number? That's really efficient to say that anyway. Okay, is there a better way to do this? I mean, because we're doing the same thing, we can probably just do this in a helper function. What is it called? Look and say So we do this, and then we just go for, oh, we want to do N. $40. And this one's $50. All right, that's the same thing. Da, da, da. You're definitely using a lot of memory doing it as a U size. It said it's always only ever going to be 1, 2, or 3. Oh, unless the value, it said unless there was another thing in here, right? So that was it. I don't know if I mentioned that in this video, but in the previous one, it said it'd always be, when I was reading through it, it said it'd always be 1, 2, or 3. So there's a potential to say, oh, let's just keep it as a character and then do this. It's this one. We need to change. Ooh, could we just do it as bytes? It'd be like, we're gonna be funny here, but we're gonna do like, does that still give me the same answer? No. Why not? It's actually way off. Am I doing this wrong? I have some byte. It might be that. Yeah. Is that right? 360154. 3798. Yeah. Oh, okay. So why was that wrong? Is because it would make these zeros and these twos and these ones, which is actually different in the Conway's Game of Life. So what I'm trying to do here is I'm gonna say, hey, I'm gonna make these into a vec of U8, and but I'm interested in just having the actual number. So I'm gonna say it's gonna be B minus the start, which is 1, plus 1, right? Because if this was a 1 and I was subtracting B1, the byte value of 1, so the literal OX31, if they were the same, it would be 0, but I want it to be a 1, so I'm going to add 1 back, a literal 1. So now these are going to be U8s of 1, 1, 1, 1, 3, 1, 1, whatever. So now I can go through the array. Does it save me a lot of time? It actually does. Let me run it a couple times just to make sure that's the case. Yeah, it does feel like it is actually faster to do it this way. So the algorithm doesn't change, but now I can just say, okay, now just push this as a U8 and the U8 value. And that will get me there. So that speeds things up a little bit. I don't know if it makes it more readable. This might be a little bit confusing. Like, we want to make it an actual integer, right? So now it's evacuate, so now we can do some stuff on it. Is there any way to tighten this up? I mean, I think we always need to create a new vector. Unfortunately. We might be able to do like with capacity. I don't know how much this helps, but if you like pre-alloc, it doesn't appear to be any faster, really. It's one of the same in the other. It may be that the default capacity is already enough. It just doesn't matter. Oh, you could have two that you're constantly just swapping between. Okay, the algorithm doesn't change much, but again, like the gist of it is you're gonna make chunks, right? So we're gonna go through and find the chunks of ones, and then we're gonna put that into our next list, and we're gonna keep doing that until we've gotten to the end. And now we've got our new thing, and we're gonna do that however many times they tell us, and then we're done. Okay, that feels good. So I'll try and I'll submit it this way. I'll be interested to see if anyone has any different solutions, did it differently, maybe in a maybe some way to make it more efficient. So that would be cool to see as well. But there you go, kind of a cool thing. And yeah, you may want to watch the video. I think I've seen it before. I'll probably still go watch it just to see. But now that we've all talked about it, I watched back in the day most of those number files. Oh, I didn't see when it was, but I haven't watched them recently, but I used to watch a lot of them. So there you go. Bye, everybody. We'll talk to you next time.